This next talk is being presented by Breaking Grounds. It's The Power of Guardrails by Colleen Dai and Grayson Hardaway.
Hello, today we'll be talking about how using secured guardrails that encourage developers to write secure code can actually decrease your risk of cross-site scripting pretty significantly. So I'm Colleen, and today with Grayson, I'll be talking about how to slash the risk of cross-site scripting in half. So I sort of want to start off with a question. What type of vulnerabilities are you seeing most often in your code? So oftentimes these are the same vulnerabilities you see popping up over and over again. And this can be a bit demoralizing if you keep finding the same types of vulnerabilities. Furthermore, with a lot of companies having a ratio of 100 or more developers to every security engineer, it's sometimes easy to feel pretty buried and like you can't actually keep up. But we want to talk about how some companies have actually been changing how they run their security programs, and it actually seems to be working for them. So they're higher leveraged and more effective at actually keeping their company secure, even while keeping the same ratio of developers to security engineers. So today we're going to be talking about secured guardrails, which are essentially safeguards put into place to make it easier for developers to do the secure thing and a lot harder to do the insecure thing. So we'll talk about how guardrails can actually drastically reduce the number of vulnerabilities you have to track down and fix, and essentially talk about some original research we've done that examines real cross-site scripting vulnerabilities in open source software. So here's a brief TLDR of what we'll be talking about today. So we used to think about eliminating individual bugs through pen testing, bug bounties, etc. But now we'll be talking about secured guardrails, which actually give you some more scalable, systematic, and long-term wins. So you might ask, how do we know this is effective? Well, we'll be talking about what other companies do, along with some research showing that secure guardrails could have prevented greater than 50% of cross-site scripting vulnerabilities in open source repositories. We'll also be talking briefly at the end how to implement this at your corporation. Cool, so who are we? I'll pass this off first to Grayson, who's going to be talking with me today.
Thanks, Colleen. Yeah, my name is Grayson Hardaway. I'm a security engineer at R2C. This is a picture of me and my lovely wife over here. In a past life, I used to work for the U.S. Department of Defense doing all manner of things, but now I work for R2C, which is a startup in San Francisco doing static analysis, along with Colleen.
Awesome. I'm also a security engineer at R2C, and I recently graduated Stanford with my Bachelor's of CS and my Master's of Statistics. And what's R2C, you might ask? So we're a SF-based static analysis startup that Grayson already mentioned, and our mission is to essentially improve software security and reliability. So all of this work couldn't have been done without the whole R2C team, so we're really grateful for them. Cool, so here's a brief outline of what we'll be talking about today. So we'll first talk about why we want to move towards secure guardrails, and then we'll talk about how do we test that secure guardrails are actually effective. And then we'll talk a little bit about what we found through our research, what we wanted to do next, and also how to eradicate vulnerability classes in general. Cool, so let's start off with talking about the OWASP Top 10. So on the left, we see this diagram, that's the OWASP Top 10 2013. And on the right, we see the OWASP Top 10 2017. And actually, the OWASP Top 10 hasn't changed since 2017, so this is essentially technically what we have currently. So it might seem a little bit similar, and if we look closely, we can see that A1 injection, sensitive data exposure, cross-site scripting are all still on the OWASP 2017. In fact, 6 out of the 10 OWASP Top 10 hasn't changed in these 4 years. So in case you're not familiar, OWASP essentially is a nonprofit foundation project, and their aim is to educate the security community and developer community about building secure software. So every few years they'll release the new OWASP Top 10, which actually represents the most prevalent in security and critical security risks to web apps. So essentially, we see that a lot of these have remained the same over the past years. And given that a lot of these vulnerability classes are occurring over and over again, we need to take a really hard look at what we're doing and how we can measurably raise the bar. So let's take a closer look of what the security industry is mostly currently doing. So the security industry has currently focused a lot on playing whack-a-mole with individual vulnerabilities. So we've been doing a lot of pen testing, bug bounties, and essentially finding individual bugs. But what we want to move towards, and what the industry is actually currently moving towards, is what we call secure guardrails. So essentially this involves continuous code scanning, enforcing safe patterns, and eliminating bug classes in general, instead of trying to eliminate individual bugs. So why should you actually trust us? You're probably thinking, where's the actual evidence that secure guardrails work? And also, the security industry has actually been finding bugs for ages, so why should we change at all? Well, we'll provide you with a few sources, including what some forward-thinking mature security programs are doing, and also add in our research, which involves preventing cross-site scripting in the wild. So let's take a quick look at what a few companies are doing. So essentially in AppSec Cali of 2018, a few people from Netflix gave this talk, and we see that they're trying to de-emphasize in their security program manual testing and traditional vulnerability scanning. And they're also trying to heavily emphasize paved road and killing bug classes in general, which is what secure guardrails is all about. And we see from this talk from Microsoft that essentially banning functions can be very valuable. We see that they actually got 41% of vulnerabilities reduced from their transition from XP to Vista just from banning string copy and other functions like this. So we know that a lot of vulnerabilities can be removed just from banning unsafe functions. And also, Google has written a book called Building Secure and Reliable Systems. And in this book, they state that it's pretty unreasonable to expect any developer to be an expert in reliability, security, and coding, and to constantly maintain vigilance when writing or reviewing code. So a better approach is to handle security and reliability in common frameworks, languages, and libraries. So ideally, libraries only expose an interface that makes writing code with common classes of security vulnerabilities impossible. So what Google is really trying to say is that security is hard, reliability is hard, and coding is hard. So it's actually pretty unreasonable for us to expect our developers to write secure, reliable code quickly. So what we want to do is we want to make our developers' lives easier, and our job is to sort of make it easier for them to write secure code and make it harder for them to write insecure code. Cool. And we can take another look at Facebook too. So what Facebook is saying is that they invest heavily in building frameworks that help engineers prevent and remove entire classes of bugs from writing code. And this is essentially what Secure Guardrails is trying to do. We also see that in their defense in-depth sort of layering, we see that Secure Frameworks is actually their bottom layer. So Secure Frameworks is actually the groundwork that underpins all their other defense efforts. And in addition to Netflix, Microsoft, Facebook, and Google, we can add on top of that our research, which finds that using secure guardrails could have prevented 59% of the 140 instances of cross-site scripting in their open source datasets. Cool. Now that we've talked a little bit about secured guardrails, let's talk about how we tested that secure guardrails are pretty effective. So we begin with a question: are secure guardrails actually effective in practice? And we realized that this question is a little bit open-ended, so we translated this into a methodology that we wanted to follow. So this became how many instances of cross-site scripting in open source repositories could have been prevented with the use of secure guardrails. So the first thing that we did was to determine scope. So we wanted to find a vulnerability that was pretty high impact, and we decided on cross-site scripting because, first of all, it is indeed very high impact. It's quite common, and web frameworks actually have standard cross-site scripting mitigations. This means that there's concrete code patterns we can look for, and it'll be easy for us to write patterns for. We also wanted to prevent cross-site scripting in our own code, of course. And if we look at the bottom of the slide, we see that the HackerOne top 10 most impactful and rewarded vulnerability types includes cross-site scripting. So cross-site scripting continues to be the most awarded vulnerability type, and it was awarded $4.2 million in 2020. So the next step after we decided that we wanted to aim for cross-site scripting vulnerabilities was to determine what languages and frameworks we wanted to support. So we chose Java, JavaScript, Python, Golang, and Ruby because these languages are widely used and very popular. And for the frameworks, essentially we chose Java JSP, Flask, Django, Express, React, Go, HTTP client, and Ruby on Rails because these are the most popular and because we believe that most people were using it and we could have a larger data set. So after this, the next question we asked is, which tool should we use in order to write code patterns and capture these patterns that we want to look for? We essentially came up with SemGrep because it's open source, multilingual, it's pretty easy to write rules and more precise than grep. We're also quite familiar with SemGrep because R2C maintains SemGrep, so we found it really easy to work with. Cool, so here's a slide about the architecture of our research. So what we did is we essentially wrote some cross-site scripting checks with SemGreps so that we could find some code patterns in Ruby, Java, JavaScript, TypeScript, etc. code in order to find cross-site scripting. We then, in order to find some open source repositories and open source code, we queried BigQuery and GitHub Advanced Search API. We used these two sources to collect a pretty large data set and then filter this data set based on relevancy. So this includes relevant frameworks, languages, and also whether it represented a true cross-site scripting vulnerability. So after that, we wrote a script in order to get the git diffs and run the SemGrep checks that we wrote on this data set. And the fourth step that we performed was triaging. We manually looked through all of this data and looked whether SemGrep should have caught a vulnerability or not. Cool. So our first step in this process was to write checks to detect violations of cross-site scripting guardrails. So the first question that we asked ourselves was, what rules should we actually create? And how can we actually define patterns for all the ways that cross-site scripting can occur? This is actually a pretty difficult question, so we relied on a few sources in order to answer this. So we looked at popular security guides, including the OWASP cheat sheets, documentation for frameworks, and also purposely vulnerable apps. We also looked into our own security expertise and used all these sources in order to define patterns. And here's an example of a rule that we wrote. So essentially, the raw function actually bypasses Ruby HTML escaping. And this can actually lead to cross-site scripting attacks, so it's better to not use this function at all. So if we look at this pattern, it's actually raw with ellipses in parentheses. And this actually captures all uses and calls to raw. And essentially, if we look at the code on the right, we see that it will actually catch the result equals raw at string call. Cool. So essentially, after we wrote a few rules and we looked into our sources to research cross-site scripting vulnerabilities and patterns, we came up with a few policies depending on the framework. So this is actually our cross-site scripting policy for Flask, and we actually run it on our own code. So the goal of a policy like this is to say, if you follow these recommendations, you're pretty unlikely to have cross-site scripting in your code base. So feel free to check out the cross-site scripting policies for multiple frameworks that we've released if you would like to see this. It's all open source and you don't need to do anything in order to see this. Awesome. So after we wrote cross-site scripting checks with SemGrep, our next step was to collect some open source data. So we went on to ask the question, how do we actually find samples of cross-site scripting in the wild? And we decided upon Google BigQuery. First of all, it's a huge data set, but it's also quick to mine. So this was one of its pros. And it's also easy to obtain a parent commit. And the reason why we want to obtain a parent commit is because we want to run SemGrep on the parent commit to see whether we would have actually caught the cross-site scripting vulnerability. But as we were scrolling through this large table of data, we actually saw that BigQuery was last updated in 2019. 2019. So the question then became for us, how do we retrieve up-to-date cross-site scripting information? We then turned to the GitHub Advanced Search API, and with this we ultimately obtained around 3,000 commits. So the pros, of course, is that the GitHub Advanced Search API is a huge data set with a lot of up-to-date data. But the cons were that it was a little bit difficult to obtain parent commits, and also that the GitHub API provides only up to 1,000 results for each search. This became sort of a pain for us later. So if we see this, we've searched for, in the messages, fix XSS as our query. And we see that it's showing 200,000 available commit results. But actually, there's around 100 pages with 10 results on each page. So it's only showing us 1,000 results, even though there's technically 200,000. So all of these results are just in the wild cross-site scripting results, and we just never were able to see all of them. So we were sad, because all of this cross-site scripting data we'll never be able to use. Awesome. So after we grabbed some open source data from GitHub Advanced Search and BigQuery, we looked at our duplicates and discarded for unrelated commits. And this ended up leading to us having under 10 commits for some frameworks. So we decided to expand the data set. We needed more data. So in order to collect more data, we used some new search terms with the GitHub Advanced Search API. So we used things like cross-site scripting, Golang, fixed cross-site scripting, Ruby on Rails, and this led to around 15 or more commits for each framework. And we were pretty happy with this because it was a reasonable starting point given our time frame, and also it would be difficult to collect more data for each framework. Cool, so now that we gathered all our data, our third step was to actually run the rules that we wrote on cross-site scripting. So we spun up an EC2 instance, gave it ample memory because we knew that there would be a lot of things downloaded in this process, and we went right to scripting. So essentially, this is the sort of process that our script followed. So it would first ingest some JSON. It would take the JSON output from BigQuery or GitHub. That included the parent commit, the commit that said fix cross-site scripting in it, and also the repository name. We then downloaded a repository on our EC2 instance and essentially got that data. After that, we got the git diffs, and essentially this retrieved the differences between the parent commit and the commit with fixed cross-site scripting on it. So after we got the differences, we ran sumgrep on the parent commit so that we could be sure whether we would have caught the cross-site scripting fix. Finally, we saved the git diffs and sumgrep results in the local database so that we could access it for later. Cool, so after we got our git diffs and ran sumgrep on the data, the fourth step was to triage. So we actually built a triager that displays the triage status up on top, and you can click whether it's a true positive or a false negative, or you're not super sure about what this actually is. And we can see that the parent commits and the fixed commits are actually side by side, and it's very easy to spot the differences. And also the sumgrep results are displayed at the bottom. So with the help of our triager, we actually managed to classify sumgrep results for each commit. And we classified the results for each commit as either a true positive or a false negative. And a true positive means that sumgrep detects the fixed cross-site scripting vulnerability, or sumgrep detects a cause that led to cross-site scripting. And a false negative just means that it's not a true positive. So I'll show you what I mean by these two cases later. So here's an example of the first case of true positive, which is detect the fix. And essentially, this is a Rails example, and we see that ERB template renders with, if an ERB template renders with HTML safe, it tells the engine, I'm super certain that this is actually safe, so please render this without escaping. And this can be very dangerous and can lead to cross-site scripting if user-based input gets passed into .html safe. Cool. So we look and see if our SemGrep rules have actually detected this fix, and then it has. It has detected the exact line. So this is an example of detecting the fix. And the second example of a true positive, which is detecting a cause, can be shown by this Django example. So this, essentially we see that this fix actually forces escaping on every email subject and body. However, this actually isn't the true cause of the problem. The true issue is that escaping has been actually turned off globally for email templates. So if you look into these lines on line 185, there's auto escape equals false for these email templates. And this is very dangerous and can lead to cross-site scripting vulnerabilities. And we see that SemGrep has actually caught this exact example. So this is an example of detecting a cause. Awesome. And now I'll pass this talk on to Grayson, who will guide you to the end of it.
Thanks, Colleen. Colleen, you've done a wonderful job explaining everything up till now, and so what I will do is carry us to the end by talking about what we found in a little bit more detail, some research next steps, and then going over how you might apply this research back in your home organizations or on your projects. So with all of the steps that Colleen outlined, by the end of all the gathering and filtering and triaging, we were left with 125 distinct repositories with cross-site scripting vulnerabilities in it. And in those repositories, we had 140 distinct commits. And so those distinct commits made up the final data set that we analyzed. And so, as you can see, there are a couple of times where cross-site scripting was fixed multiple times in the same repository as a result. Of those 140 commits, the SemGrep rules that we applied trying to detect cross-site scripting had a positive hit 82 times for a detection rate of about 59%. And so here's a chart that summarizes the data. So the actual magnitude of the bar is the number of commits that we had for that language plus framework. The blue is a true positive for that commit, and red is the false negative for that commit. And so a couple things that I want to highlight here are on the far left, you can see that we only had a very small number of Go repositories. Turns out it was really hard for us to find cross-site scripting instances in Go, and I'll talk a little bit about our hypotheses of why that is later. And then, of course, on the far right side, we see that client-side JavaScript, which is JavaScript that runs in the browser. This is in contrast to regular Java, or not regular JavaScript, but like JavaScript that's in Node.js, like a server or some other kind of environment. Anyway, client-side JavaScript had the most cross-site scripting instances by a long shot. And then you can see that Java and JSP had the highest detection rate. It's the largest blue bar inside of it. And you can see that our ExpressJS rules had the lowest detection rate, which is the largest red bar. And so this is a tabular view for those who prefer the tables. It's sorted by detection rate. And so once again, you can see that Java and JSP is at the top, ExpressJS is at the bottom, and everything else is in between. So I want to highlight a couple of more examples of things that we found. Colleen already demonstrated a couple when we were talking about our definitions of true positives. So I'll just highlight a couple more because they're very interesting. So this is one of our Go examples, one of our 3. And so what's happening in this one is you can see that the committer has removed this line that writes a string or a stream of bytes directly to the response writer. And instead what they have done is they've replaced it with this error template that is then rendered into the response writer's stream instead. And so the reason this fixes the cross-site scripting vulnerability is because writing data directly to the response writer doesn't provide any escaping whatsoever. It has no context. It doesn't know anything about HTML. It just writes what you write to it. And so instead, by switching over to the HTML template package and calling execute on a template that you define, This package is designed to be safe as it can be, at least, and will provide escaping for the HTML input that gets rendered in that template. And so this is safe. It fixes the cross-site scripting vulnerability. But in any case, this is one of the examples of detecting the exact line, because our semgrep rule detected the direct write to the response writer. It picked that up and then flagged it here. So this is another example. This is a Java and JSP template example. So the committer here has removed or has added this special tag that starts with C:out and has a value contained within it. And so in JSP templates, C:out will automatically escape whatever is contained within that tag. And so this is one of the few correct ways of making sure that your data is escaped in JSP templates. JSP templates are particularly interesting because, insofar as we can tell, there's no actual automatic escaping enabled in the default ecosystem. And so by default, nothing is really rendered safely. And so you have to remember to do C.out or C:out in one of the other alternatives that do escaping for your data in JSP templates. And so we can see the semgrep results here, where it happily picked this up. It noticed that these values were being rendered directly and were not being rendered in a safe way. And so, of course, we had a handful of instances that we did not detect as well. And so I just want to show you one of those here. So this is one of our Express.js examples. And what this Express.js app does is have a special function for rendering errors in a fancy little SVG that they've put together. And so the way that they construct this SVG is by manually constructing HTML using a JavaScript template string. And so you can see that the line that is updated has a message template variable within it, and this render error function gets called in several places in the application. And in a few of those places, those messages are susceptible to user input, which means you could technically inject something into this and do cross-site scripting. So of course the fix is here that the committer does is encoding HTML. The reason that semgrep wasn't able to detect this in particular is because we didn't have a way of inferring that HTML was being manually constructed in a template string. And so if you detected every JavaScript template string in the dataset, obviously that would be too much and it wouldn't be very precise and not very useful. And so since we weren't able to do that, we weren't able to detect this. So we learned a lot through this research, and it was very interesting to sort of take a slice of the open source ecosystem for cross-site scripting and to take a look at it. And so I want to talk about some key takeaways. Our first one is that we believe that secure guardrails would work. And so the idea, of course, is that if these committers were running secure guardrails with these policies that said, don't do this instead, that a lot of these instances would have been protected against. So overall, we had a 59% detection rate with the policies that we developed. And one anecdote that I want to draw special attention to is that our React data, the data that we ended up getting as a result of running all these rules on React, ended up being 41%. But the only rule that we were running on our React data was just looking for dangerously set inner HTML. And so that means out of the 12 or 13 instances that are there, nearly half of them were just caused by improper use of dangerously set inner HTML, which, of course, by the name, dangerously bypasses your cross-site scripting protections. And so this is actually almost an identical percentage to what Microsoft got with banning stir copy. And so, seeing these results is really interesting and leads us to believe that you can go really far just by enabling these really simple guardrails, such as disabling or preventing use of dangerously set inner HTML. So the other 59% of that data set was frequently a third-party library that eventually rendered a component with dangerously set inner HTML. And so we didn't write rules to cover every third-party library in existence because that would have taken forever. And so, but the culprit was still usually dangerously set inner HTML. It just traveled through a couple of code paths. Another takeaway is that having no guardrails is a recipe for disaster. This is particularly highlighted in the results for Java and JSP because, to our knowledge, JSP provides no escaping by default, aside from some plugins that you can use. So if you are responsible for this technology, I highly recommend you go look at these plugins. Anyway, by default, JSPs do not safely render anything, which means it's totally on you or your developers to remember to escape things properly. So Java and JSP is not secure by default, nor does it make the safe path very obvious. And this was reflected in our results where we were able to get a really high detection rate in Java and JSP. And then Colleen talked about this way back at the beginning of the talk, but as we developed these sets of rules to use for this research, we wanted to use these checks on our own code, of course. And so we have a Flask backend for one of our projects. We deployed our Flask policy on that. And to date, as of, it's been running for about 3 months, it has detected and prevented 2 cross-site scripting instances that I know about from going out into production. So we've been able to get mileage out of it ourselves, which has been really awesome. Other takeaways that are less related to the actual results. Of course, there were only 3 instances of cross-site scripting that we found across all of our searching in GitHub and BigQuery. Only 3 samples were we able to find, which leads us to think that either like nobody writes web apps using the frameworks that we search for, or cross-site scripting is just really hard to do in Go. We've looked at Go a number of times for a number of different other things, and it typically has the safest track record. And so that it could be that it's just harder to do vulnerabilities in Go than other things. Of course, on the flip side of that, cross-site scripting occurs most often in client-side JavaScript. There were a total of 44 commits fixing cross-site scripting, which was nearly a third, 31% of the entire corpus that we had collected. Of note, in these 44 commits, 17 of them were strictly due to assignment to inner HTML. And so that was 40% of all of the client-side JavaScript findings. So you can get a lot of mileage out of just like checking to make sure that people aren't assigning things to dangerously set inner HTML or inner HTML, and that would go really far. And so this is an example of one of those inner HTML assignments. You can see that they're manually constructing HTML and then directly assigning it to inner HTML, which creates a cross-site scripting vulnerability. Some considerations here, of course, are that we didn't have any measurements for false positives. We wrote our checks as sanely as possible. So like we didn't try to detect 100% of Java, for instance, because that would have given us a 100% detection rate, right? So we were sane in how we approached this. We didn't like try to cast a wide net. We weren't trying to like fudge the numbers or anything like that. But one of the other reasons that we didn't really focus on false positives for this research is because we think that false positive reduction would yield similar results, because the iteration process on reducing false positives for a check strictly takes your total result set and tries to weed out things that were not true positives initially. So we think that the true positive results would be approximately the same, and the detection results would be pretty much the same as well. So what do we want to do with this next? Obviously, we want to apply this to more languages and frameworks. We found it useful for us just on our Flask backend, and we want to apply that to other things as we become aware of them or interested in them. And then, of course, we also, as I just mentioned, want to spend some time reducing the false positive rate for some of the checks. We have methods of doing this at R2C. We have like a massive code scanner that goes out and finds a bunch of stuff, so we can we're pretty confident in our ability to do false positive reduction. We also want to cover additional vulnerability classes. Obviously, the OWASP top 10 is a very easy list for us to target. And a couple of the ones that we've done so far, in addition to the cross-site scripting ones, are command injection, SQL injection, and unencrypted transmissions. And so if you're interested in actually running any of these rules, SemGrep is open source, and you can download them. You can download SemGrep, and you can download these rules for free if you want to scan your own code for these things. One other thing that we want to do is prove this approach on private code. So obviously this research focused exclusively on open source research, but we really want to make it applicable to people who are trying to run security organizations. And so we want to see how this process holds up on private or internal code. So some questions that we would need to answer for that are like, do companies use internal frameworks rather than open source ones? So since everything we did was open source, if there are internal frameworks that need custom rules written for them, like how would this apply to that? And then another question is like, are there organizational challenges to adopting secure defaults, secure guardrails, excuse me, at scale? And so, sometimes it's hard to roll out new checks. It's hard to roll out checking programs. And so what sort of political barriers or technical barriers are there inside of an organization? So I want to conclude this talk by talking very briefly about how you can take this back to your own organizations. And so how you might do this, we propose this 4-step process for how you might take this eradicating vulnerability classes back to your own organization. So the first step is to select a vulnerability class, of course. You have to pick one. There's a lot to choose from, and there are a lot of different ways of choosing which ones you want to focus on. And so if you have vulnerability data, like a vulnerability management program, you can rely on that to tell you which vulnerabilities you experience most frequently, or perhaps which ones have the highest impact. And then you can select one and start to move down this process. And so the second step is to select safe patterns and make it the default. And so this is that policy that we showed you earlier. It looks kind of like this. So you have to identify what are your secure guardrails, what don't you want your developers to do that would result in the vulnerability, and then identifying what the alternatives are, the recommendations for them. And then you have to make that the default pattern in some way. And so some ways to do that are steps 3 and 4. Step 3 is to train developers to use the safe pattern, get the word out, use your CI/CD pipelines if you have the ability to inject messages into that while you scan for code patterns, do that. Otherwise, hold like brown bags with your developers, or if you have any security training or onboarding, mention it there. Any coding guidelines that you have as well can be updated with this. Those are great places. And then we humans are fallible, so even if we've had this beaten into us, we still forget things. And so you have to use technology to enforce the safe pattern. And so this would be using some sort of linter or like text scanner to regularly enforce that these patterns don't get into your code. So usually this happens at like CI/CD level or build time, something like that. Once again, this is an example of that policy. So this is kind of what it looks like when you're finished. All of these things have corresponding like linter rules that get run and check your code on a regular basis. If you're interested in the cross-site scripting checks that we wrote for each one of the frameworks that we mentioned, we've publicized them all for free because we did a lot of the work. And if you want to benefit from that work, we figured why not? So here you go. You can check out the policies like I was just showing you at semgrip.dev/docs/cheat-sheets, and they will all be there. And if you're interested in more details about how you can take this back to your organization, I'll refer you to a talk by 2 of our colleagues, Clint Gibler and Isaac Evans, at Global AppSec San Francisco 2020 about eradicating vulnerability classes. And so this was a very high-level overview of that. They go into way more detail here at this talk, so if you're interested, please check it out. And so with that, we will conclude our talk. Please join us in the Discord channel for questions, and we hope to see you there.
Great presentation. Thank you so much for participating in BSides Las Vegas this year and submitting this talk. I was really excited when I saw this talk on the CFP, so thank you so much.
Thanks.
For those of you, watching this in the Discord, if you have questions for the speakers, now is the time to speak up. I am monitoring the Discord. I will ask the questions as you ask them. I also have some questions that I want to ask since I watched the talk. So just throw your questions in the Discord, and I'll ask the speakers. Well, one of the questions I like to ask speakers is what was the hardest part of this research for the both of you?
Yeah, I'll start. Then, Colleen, do you want to add your thoughts after? The hardest part for this was probably triaging all of the results. So we downloaded a ton of data, and we got the diffs between the parent and the fix and had to look at each one and compare that with the results of our scanner in order to make sure that it was like accurate. That took a long time, and occasionally there was debate about what it meant to be like a true positive versus a false negative or something similar. So it was a Herculean effort, and there was a team of people involved with it, not just the 2 of us. But that was definitely the most challenging part, I think. And even now, I'm not certain that we got every little bit right. when we triaged everything, but we did our best.
Yeah. How many diffs we talking about? I'm just curious. The number you mentioned, lots of diffs. Just curious.
Yeah. So we ended up with like 140 distinct commits, and that was after manual review of about 700 commits. But we started out with a bunch. I think there was like somewhere between 3,000 and 5,000. But we ran some like deduplication and heuristics on that first in order to get us to the original 700. But like manually, like our team looked at probably 700 different diffs throughout the entire thing.
Oof. Fun. All right. What surprised you both the most when you started doing this research?
What surprised when we started? I think the most surprising thing was probably the difficulty of getting the data, because it seemed like it was such an easy thing to get. And we talked about it in the talk, obviously, where there's a limitation with the GitHub API. We didn't show this in the slides, but we actually talked with like a GitHub engineer, and we were like, hey, could you like give us like your insider access to this API? And they were like, oh no, we can't do it either. We can only access 1,000 results. We were like, oh, so like it's limited. You cannot do any more than 1,000 results from a query.
Oh, interesting. You mentioned in your talk, looking at the parent commits. What would you say the purpose of scanning the parent commit is versus the fixed commit?
Yeah. So if you think about it, the fixed commit doesn't actually have the vulnerability in it. And so we needed to be able to scan the parent commit, which is any commit prior to the vulnerability being fixed, in order for the scanner to pick up the actual code pattern that would have indicated the vulnerability. So sometimes, depending on how the vulnerability was fixed, the fixed commit would have been sufficient. But in order to get 100% of the time, we scan the parent commits.
Okay. If a corporation, so at the end of the talk, you mentioned a slew of recommendations. I work for a large enterprise who's also cheap. So, if we could only implement, one or a handful of your recommendations, which ones, would you say would be the most important ones to implement, and why?
Yeah. If you have the capability to get a scanner up and running in a continuous fashion, it doesn't necessarily have to be in a CI/CD pipeline. You could also do it with, like, if you use Git pre-commit hooks out to all of your developers. But as long as you're getting some scanning done with a policy that's you've either developed or has been developed for you, because we made all of these rules free, for instance, that's probably the number one recommendation, is like use technology, leverage it, and hopefully that will help the most.
Colleen, do you have anything to add? Yeah.
Yeah, it's a little bit like having security reviewer constantly checking. Like that's the whole idea of it, is like making sure that something or someone is reviewing something all the time.
Right. Nice. If I work, I'm not saying I do, but if I worked for a company that's never done, lots of industries are finding out cybersecurity is important now. So, if I work for a company that's never done this type of thing before, and I have a 10-year-old code base that's never been reviewed, what do you each recommend?
Yeah. I don't know if this is true. I imagine for situations where somebody's responsible for a Java stack similar to the one that we talked about in the research, this could be the case. And one of the things that stuck out to me is that it's difficult to use the technology to your advantage. There's no way of automatically escaping stuff in that tech stack, or at least that we're aware of. However, there was a really cool plugin that we had found that will automatically escape the JSP templates for you, as long as you set up your Java code base in order to use that plugin. And so my recommendation would be to look for something like that. If you have the ability to use a plugin or a library of some kind that automatically makes your stuff safer, makes it harder to do the insecure thing, I would definitely recommend that. And so if that's not possible for some reason, if you don't have a library, scanning is like the second best thing. And so if you can scan for common gotchas, do that. And then you won't have to worry about whatever gotchas you're scanning for anymore.
Nice. All right, I'm going to switch gears a little bit here. What excites you the most about this type of research?
Yeah, at the end, we talked briefly about false positives, and I, in particular, am typically excited about reducing false positives. And so, we at R2C are the maintainers of SumGrep, which is the scanning tool that we used. And so from this, we now have the ability to build in some features to our own tool to help us with false positive reduction. And so in particular, one of the examples that we talked about that we couldn't find typically was HTML being constructed in a JavaScript template string. And so our program analysis team recently added, or is adding, I don't think it's added yet, is adding HTML as a language to our scanner. And we also have this neat ability where we can extract pieces of code and feed it into a different parser. So in this case, we would be able to extract the template string, feed it into the HTML parser, and if it parses, then we can scan for the template variables. And if we find that, then we can reliably report that as a true positive, much more so than not being able to find it at all, which is our current capability. But this is in the works, and I'm really excited about being able to deploy this cool tech in order to find this stuff.
Nice. Colleen? Nice. Okay. So, last question here. Where can people find, the tooling and your research that you were talking about?
Yeah, for sure. So we have the data set on GitHub, or a link to the data set on GitHub, as in addition to all the code that we used to process this stuff. So I'm going to post that in the Discord now. There's a couple of things that we're still working on in order to like make this a little bit more accessible. We wrote an article about this research a couple months ago, but honestly, it just didn't turn out very well. Like, it didn't meet our quality bar. And so we actually found that doing the slides and the presentation was a lot easier than doing the article. So there will be an article that will be coming out soon. It will be linked in the README in the repository that I just linked. But for now, most of the relevant information is in that GitHub repository.
Great. Well, thank you so much. Thank you for being a part of the BSides Las Vegas campfire. And if people have questions, they can still reach out to you on Discord. And thank you so much.
Cool. Thank you.